Take a standard piece of aerospace aluminum and add an almost microscopic dusting of this metallic powder to the mix. That tiny fraction of a percent strips away dead weight while building an unyielding, heat-resistant strength. Yet, if you try to mine it, you won't find a single pure vein of it anywhere on Earth. In nature, it hides. This is scandium, element 21. Its properties lie within its highly reactive outer electron shell and its tendency to form a stable +3 oxidation state, allowing it to bond with other metals. For decades, it existed only as an elusive scientific theory. Today, it quietly holds modern rockets and spacecraft together. In the late 19th century, Russian chemist Dmitri Mendeleev looked at the known chemical world and mathematically insisted that unseen elements must exist. Constructing his original periodic table, he identified a distinct structural void between calcium and titanium. He named the missing occupant Eka boron. Mendeleev calculated an atomic weight of roughly 44 for this empty space. He described how the invisible metal would react with oxygen and acids. 10 years later, in 1879, Swedish chemist Lars Fredrik Nilsson was analyzing the rare earth minerals euxenite and gadoliniite from Scandinavia. Deep within the rock, he isolated a new oxide. Its mass was 44.9. Its chemical behavior matched Mendeleev's calculations. This discovery validated the periodic table's predictive power, transforming the gaps in Mendeleev's chart from mathematical guesses into reliable blueprints for missing matter. The problem with scandium is its isolation. It is distributed across the entire planet, trapped in over 800 different minerals, but always in trace amounts. It almost never concentrates into dense, mineable deposits. Industrial engineers cannot simply dig for it. They have to sift through the leftover tailings of massive commercial mines, acting as scavengers. To yield even a few kilograms, operators put the caustic waste sludge of titanium, uranium, and rare earth mining through complex chemical refining processes. The Earth holds plenty of scandium. The high cost stems entirely from its chemical refusal to gather in one place. That investment pays off the moment scandium meets aluminum. Mixing in a fraction of a percent refines the aluminum's grain structure, preventing microscopic cracks from forming under stress. This creates a superalloy that remains rigid and immune to corrosion. It allows engineers to shave pounds of metal off the bulkheads of military aircraft without sacrificing structural integrity. In orbital rocketry, where every extra ounce of mass costs thousands of dollars in fuel, shedding weight from the chassis dictates whether a mission is financially viable. These same physical tolerances apply to elite sports. Competitive bicycle frames, professional baseball bats, and golf clubs utilize scandium alloys to transfer kinetic energy without bending. In additive manufacturing, precision lasers fuse scandium aluminum powder layer by layer. The resulting 3D printed components are lightweight and highly resilient. Beyond structural support, mixing the metal with iodine creates scandium iodide. Inside metal halide lamps, this compound emits a broad spectrum of light that closely mimics natural sunlight, illuminating night games and television broadcasts. And inside high-temperature solid oxide fuel cells, stabilizing zirconia with scandium tightens the crystalline lattice. This allows electrical current to pass through the system with far greater efficiency. Because pulling it from the ground is so difficult, scandium is strictly reserved for the highest stakes human engineering. For all the structural rigidity it provides in an alloy, isolated scandium metal in its pure state is surprisingly soft. It has almost no structural strength of its own. Its physical capability only emerges through its chemical interaction with the metals around it. As the global economy pivots toward electric vehicles and scalable hydrogen fuel cells, the demand for lightweight, highly conductive components is accelerating. Scientists are now pushing to develop more efficient chemical solvent processes to filter scandium from industrial waste streams and drive down the market price. An element that Mendeleev identified as a blank space on a piece of paper now serves as a key material in the drive to make deep space exploration and clean energy more weight efficient.